Our next programming project is laboratory exercise M10, integer arithmetic, using high-speed multiplication and division by powers of 2. And as we go through this exercise, we begin to examine the properties of various bit shifting instructions. I am going to make a copy of the previous laboratory project M09. So the new name is M10. Because we will continue using input-output library to communicate with the user and display results of computation. I'm just going to open this project. And go to Solution Explorer and finish renaming it at the level of the solution. And project name and the actual source file, which will contain the solution for this exercise. Of course, we should maintain the proper names. Prototype program for M10. That is correct. So now I'm just going to do a little bit of cleanup. All I need to do is include io.h. We will use other definitions in our constant segment. I will also replace all of the data segment. And of course, I'm just going to remove all of my code from the main procedure and also remove the procedure make beep at the end of it. So overall, this is just a skeleton set of segment directives for constant memory segment data, global data, and the code. So of course we're going to have at least a return instruction here to return back to the caller from the main procedure. Shift left instruction performs a logical left shift on the destination operand. Okay, so for instance, if we have we could use an example of this. We could say shift left like this, and we can specify a register AL, for instance, and specify that we want to shift everything to the left, just one. So this is the number of shifts to perform, and what is going to happen in this register. So this is an example of our register. Let me adjust the sizes of my windows. So as we perform this instruction, so if this is our register AL, the initial set of everything that it has, basically this entire set of bits, is shifted to the left, and so this the bit that is shifted out of the space is placed inside the carry flag. So the carry flag gets filled with the bit that moves out of the available space, and 0 replaces the rightmost bit, the lowest bit in this register. So this is how it works. And so the possibilities are that we can the first operand of shift left is the target, right, the destination of the instruction, and the second operand specifies the count, how many times to shift. The count, of course, has to be in range So basically for an 8-bit size destination, the maximum times you can shift is actually 7. So this is the highest number, and the lowest number is 0. Okay, so shifting by 0 is also permitted. In other words, it's okay to say shift 0. No shift will be performed by the instruction. Or if we can say shift 7, then we're going to, you can count it here so that we have the lowest bit right here. So we're going to shift 1, 2, 3, 4, 5, 6, 7 times. So basically what happens if we specify the maximum shift number is that we'll be moving this bit from here from the lowest to the highest bit. Naturally, because the shifts are performed sequentially, all of these spaces right here will be filled with zeros, and the final, this last, basically what we're going to end up with is that this bit, the second bit, or the bit with index 1, will be shifted to the carry flag. Okay, so this is what's going to happen if the shift count is 7, and the lowest bit will be placed right here. The rest of from the beginning to this bit right here, all of this space will be filled with zeros. So it's pretty simple. So it works quite consistently, but there is one limit, is that the count can be either immediate value like I used, or it can be register CL. Okay, so if you need the variable, only register CL is accepted. The destination, the target of the bit shifting, it can be in memory or it can be a register. So both memory and register can be shifted by this instruction. So this is an example of the shifting instruction. So we have certain bit pattern in register BL, and what we do is that, so basically this is hexadecimal 8F, and we shift it once. So we just say that let's shift it once, and of course the highest bit right here is going to be shifted into the carry flag. Everything else is shifted to the left, and because we shifted only once, it's just one shift, and the rightmost bit is set to 0. So one of the best uses of shift left is performing high-speed multiplication by powers of 2. So we can assume that shifting any operation or any value left by n bits multiplies the operand by 2 raised to the nth power. For example, shifting a value 1 bit to the left yields the product multiplied by 2. If we shift by 2 bits, we're multiplying it by 4, and so on. So this is an example that basically we take 10 and multiply it by 2 raised to the second power if we shift it by 2 bits. So it's 10 by 4, so the result is that EAX will become 40. So shifts are more efficient to execute than corresponding multiplication and division instructions. Some multiplication instruction could take a lot of clock cycles, so shift left executes only 1 clock cycle. It's pretty efficient and requires just much fewer bytes to encode. So whenever possible, the shifting instruction perform multiplication whenever we have division multiplication by powers of 2. And if you take a side experiment and create a small C program and just try to create like an integer x, say that we can use the same example as here, set it equals to 10, and then try to set x equals x multiplied by 2, or try For instance, also try to take x and multiply it by 3, and then try to multiply it by 4. And if you compile this type of program, I'm just using semicolons here because it's just a comment in my assembly program. But if you try a program like this, I can assure you every time you're multiplying by powers of 2, your C++ compiler, C and C++ compiler will generate a shift left instruction. Likewise, if you'd be dividing by 2, if it'll be using shift right instruction. In case like this, where it's the multiplier is not a power of 2, it will be using a multiply instruction, which we will cover in our next laboratory exercise.